Hello, welcome to another module in this massive open online course on the principles of CDMA, MIMO, OFDM wireless communication systems. In the previous module, we have seen the properties of the PN sequences employed in a CDMA communication system. Let us now look at the bit error rate performance of a CDMA system. So today in this module, we are going to look at the bit error rate of a CDMA system. So what we want to look at, we want to look at the bit error rate of the BER or the bit error rate of a CDMA system. For this purpose, consider a single user CDMA system. Let the transmitted symbol denote the single user by user 0. So, we are calling this user as user 0. Let the transmitted symbol of this user be equal to A0. So, A0 is the transmitted symbol and the code CDMA code be denoted by C0 of n. So, the code of user 0, so the code of user 0 is C0 of n, and each C0 of n, as we have seen previously, is either plus or minus 1, and we are considering a code length. Let the code length be equal to, so we are considering a code length of n. Okay, so we are considering a single user CDMA scenario in which the transmitted symbol of user 0 is A0, the code of user 0 is C0 of n, and each code symbol or each chip is plus or minus 1, and the code length is capital N. Alright. Now let us look at the bit error rate performance of this system. Now we know that the transmitted symbol xn xn is given as xn is equal to A0 times C0 of n, that is, this is the symbol multiplied with the code. In a CDMA system, we said that the transmitted symbol is the symbol of the user multiplied by the code. Right. So, we are generating the transmitted symbol xn as the symbol A0 times the chip or times the code, that is C0 n. Okay. And now the received symbol, therefore, our received symbol yn is given as h times xn plus wn, where h is the, everyone remembers that h is the fading coefficient. In particular, we are considering a Rayleigh fading channel. So, this is the Rayleigh fading channel coefficient, and each wn, we are assuming each wn is IID Gaussian noise such that with variance sigma w square, with variance sigma square. So, we are saying yn equals h times xn plus wn, where h is the Rayleigh fading channel coefficient, xn is the transmitted symbol, and wn is the IID independent identically distributed Gaussian noise sample with 0 mean and variance sigma square, that is expected magnitude Wn square, or the power of the noise is equal to sigma square, and also the noise is 0 mean. Therefore, expected value of Wn equals expected value of Wn is 0. Further, the noise is independent, which also means uncorrelated. Therefore, we will have expected value of Wn times Wm conjugate is equal to 0 if n is not equal to m, and this follows from the independence of the noise samples. The noise samples are independent, which means the noise samples are uncorrelated. Therefore, if we look at two distinct noise samples Wn and Wm, expected value of Wn times Wm conjugate is equal to 0. All right. So, the expected value of the correlation between these two different noise samples is basically equal to 0. So, the noise samples are Gaussian, they are independent, identically distributed, each has power or variance sigma square, each is 0 mean, and since they are independent and 0 mean, it follows that the correlation between two distinct noise samples is equal to 0. Okay. So, this is the system model that we have, this is the standard system model. Now, let us substitute our CDMA symbol. We have Yn equals h times xn plus Wn, but xn is equal to a naught times c naught n. We have already seen that, that is the product of the symbol and the code, and as a result I have Yn is equal to h times a naught c naught n plus Wn. Therefore, this is the system model, or this is the system model for our CDMA wireless communication system. Now, at the receiver we have to correlate, as we have seen for CDMA, we have to correlate with the code of user 0. So, at the receiver we process correlate with the code of user 0, which means I have to perform 1 over n summation Yn c naught of n, that is element wise multiplication, sum, and finally divide by n. This is my correlation with code c naught of n, and this is equal to, now I will substitute the expression for y of n, and this is equal to summation of n. Y of n is h times x of n, which is h times a naught c naught n plus Wn times multiplied by c naught of n. And now, when I expand the bracket and simplify, I am going to have 1 over n summation over n h times a naught c naught square of n plus 1 over n summation over n Wn c naught of c naught times n. which is equal to, again let me simplify this further, 1 over n, I can, because h and a naught are common, I can take this outside, summation, or I can write this as follows, I can write this as h times a naught 1 over n summation of n a naught c naught square n plus 1 over n summation over n w n c naught over n, and now this is our signal part, and this is our so what we have done, basically we have substituted for xn is equal to, or basically we have substituted for xn, right, we have substituted for yn is equal to h xn plus wn, but xn is a naught times c naught of n. So, we have substituted for yn equals h a naught c naught n plus wn in this expression for the correlation, and we have simplified this resulting expression to derive the expressions for the signal part and the noise part. Now, if you look at this, if you look at the signal part, we have 1 over n summation over n c naught square of n. Now, if you look at this, this part is equal to 1 over n. Now, let us look at this n c naught square of n, but each c naught of n is equal to either plus or minus 1, which means c naught square, which implies c naught square of n is equal to 1. Therefore, this is equal to 1 over n summation over n c naught square of n is 1, which is 1 over n times n, which is equal to 1. And therefore, now we substitute this expression here in this sum 1 over n summation over n c naught square n, I get my y of n is equal to h times a naught plus 1 over n summation n equal to 0 to n minus 1 w n c naught of n, and this is basically the signal part. So, the signal is h times a naught, and this is the same as before, this is the noise at the receiver. So, we have again simplified this after the correlation in terms of the signal part and the noise part, and we are seeing that the signal part is simply h times a naught, that is the signal part. Now, let us look at the noise part, let us try to simplify the noise part and see what intuition we can get. Let us denote this by w tilde, w tilde is 1 over n summation over n w of n times c naught of n. Now, let us look at the expected value of w tilde. Expected value of w tilde is expected value of 1 over n summation over n w n c naught of n, which is equal to 1 over n summation over n expected value of w n times c naught of n, but expected value of w n is 0, since w n is 0 mean noise. Therefore, this is basically 1 over n times 0, which is equal to 0. Therefore, we have expected value of w tilde equals 0. Therefore, w tilde also has mean equal to 0. Since each w n has 0 mean, w tilde also has mean equal to 0, correct. Now, let us look at the variance of this noise. Variance is expected value of w tilde conjugate, which is expected value of 1 over n summation over n w n C naught of n times 1 over n summation over m w, let us consider w conjugate of m C naught conjugate of m, which is equal to expected value of 1 over n square summation over n summation over m w n w conjugate m C naught n C naught conjugate m, which is equal to 1 over n square. Now, taking the expected value inside summation over n comma m, expected value of w n w conjugate of m C naught n C naught conjugate of m. Now, we know that expected the noise samples w n and w m are independent. Therefore, we have already said that expected value of w n into w m conjugate is equal to 0 if n is not equal to m. Therefore, only those terms in this summation will survive where n is equal to m. Therefore, we can simplify this as 1 over n square summation over n expected value of w n into w n conjugate, which is expected value of magnitude of w n square times C naught n into C naught n conjugate, which is C naught square of n, since C naught is a real quantity. But we know that expected value of w n magnitude square is the variance of the noise sigma square. Expected C naught square n is equal to 1, since C naught is plus or minus 1. Therefore, we know that this can be simplified as 1 over n summation over n sigma square times 1 or 1 over n square, and therefore, this is equal to 1 over n square sigma square times n into 1, which is 1 over n square into sigma square n, which is sigma square divided by n. Therefore, expected w tilde magnitude square or the noise power is equal to sigma square divided by n. Therefore, we are finding something very interesting. We are finding that this noise w tilde at the output of the CDMA receiver after correlation, the noise is 0 mean, the variance is sigma square divided by n, that is the noise power is decreased by a factor of n. Therefore, the noise variance is suppressed or noise power decreased by a factor of n. Okay. So, now we have our net system model. Remember, our system model equals is y of n is equal to h times a naught plus 1 over n summation over n w n C naught of n, and this quantity we called as w tilde. So, this is equal to h times a naught plus w tilde, where the variance of this w tilde equals sigma square divided by n. Now, let us look at the signal power. Signal power equals expected value of magnitude h square magnitude a naught square, which is magnitude h square times expected value of magnitude a naught square but expected value of magnitude A naught square is simply the transmitted power. So, the signal power is P times magnitude of h square. So, the signal power is P times magnitude of h square, where h is the channel coefficient. Therefore, the SNR or the signal to noise power ratio, the SNR or the signal to noise power ratio is the signal power, that is magnitude h square P divided by the noise power, that is sigma square divided by n, which is equal to n times magnitude h square P divided by sigma square. And therefore, now you can see there is a factor of n, that is the signal to noise power ratio is amplified by a factor of n in this CDMA system. This is a very important aspect of a CDMA system. In a CDMA system, this which is arising due to the spreading code of length n, this processing, this gain of n which is arising due to the spreading code of length n, this is known as the spreading gain or the processing gain of the CDMA system. So, this factor of n increase in the SNR is known as the spreading gain or the this is known as the spreading gain or the processing gain of the CDMA system. This is a very important aspect of a CDMA system. The spreading code is resulting in a gain which is known as the spreading gain or the processing gain of the CDMA system. Right. Now, let us look at the bit error rate of this CDMA system. Let us look at the bit error rate. Previously, we have seen the bit error rate of a normal wireless communication system. So, now let us look at the bit error rate of a CDMA communication system. We observe that the SNR at the receiver, our SNR at the receiver is magnitude of h square times n p over sigma square, which is magnitude of h square times n times p over sigma square, but p over sigma square is the SNR at the transmitter, which we simply denote by SNR. So, this is basically magnitude of h square times n, which is the processing gain, times our SNR. So, this is the same expression before that we have seen for the relay fading channel, except instead of SNR we have n times SNR. Therefore, the bit error rate, using the same expression as before for the bit error rate of a BPSK system across a relay fading channel, we can write the bit error rate of this system as the bit error rate of this system equals half 1 minus square root of n times SNR divided by 2 plus n times SN, n times SNR, and approximately this is the exact expression. This expression is the exact expression, and approximately as we have seen at high SNR, this is 1 divided by half 1 divided by 2 times n times SNR. I have to replace SNR in the previous expression by n times SNR, and this is the approximate bit error rate expression. So, my exact bit error rate of the CDMA system is half 1 minus square root of n times SNR divided by 2 plus n times SNR, and the approximate expression at high SNR is 1 divided by 2 times n times SNR. This is valid at high SNR. So, this is at high SNR. Okay. All right. So, this is the bit error rate expression for the CDMA system. Let us now look at an example to understand this better. So, let us look at a simple example to understand. So, this simple example is for the bit error rate this is for the bit error rate of the CDMA system. Now consider CDMA system with n equal to 256, that is code length n is equal to 256, and my SNR, that is the transmit SNR, equals P over sigma square equals 15 dB. This is the SNR in dB. What is the bit error rate of this CDMA system? Bit error rate of CDMA system over a what is the bit error rate of the CDMA system over a relay fading channel. Alright, so this is the question that we are asking, that is to calculate the bit error rate of the CDMA system, in which the dB SNR is 15 dB and the code length of the spreading code is n equal to 256. Okay. And now we can calculate the bit error rate as follows. We have the expression for the bit error rate, as we have already seen, is given as bit error rate is half times 1 minus square root of n times SNR divided by 2 plus n times SNR, fine, okay, and we have n equal to 256. My SNR in dB equals 15 dB, which means 10 log 10 SNR is equal to 15, which means SNR is equal to 10 to the power of 1.5, which is equal to 31.623 approximately, and therefore the bit error rate equals half into 1 minus square root of 256 times 31.623 divided by 2 plus 256 times 31.623, which is equal to 6.175 into 10 to the power of minus 5. Therefore, my bit error rate equals 6.175 into 10 to the power of minus 5. So, what we have done is we have calculated the bit error rate of the CDMA system with a spreading code length of n is equal to 256 and the dB SNR is 15 dB. We are saying that the bit error rate of this system is 6.175 into 10 to the power of minus 5, that is the bit error rate of this system. So, what we have seen in this module is we have seen how to compute the bit error rate, that is what is the system model for a CDMA, that is the input output system model for a CDMA wireless system, and how to compute. We have seen another important aspect, that is the processing gain or the spreading gain at the receiver arising from the correlation with the spreading code in this CDMA system, and finally we have seen what is the expression of the bit error rate for this CDMA system in a relay fading channel, and we have done a simple example to illustrate this principle or how to the procedure to calculate the bit error rate of a CDMA wireless system. So, we will conclude this module here and we will look at other aspects in the subsequent modules.